that's what I was saying.
Oh.
Yeah.
Okay, so what
M
is
N
N?
doesn't make a difference. Huh?
What is N and M exactly? What does that mean?
That's just an index. It just counts. It just tells you where your bright fringes are and your dark fringes are.
Oh, okay.
Okay, so this is N equals 0. This is N or M equals 1. M equals 2, 3, 4, and so forth. That's why I was counting that there. And what it indicates here is whole wavelengths. Okay, N times lambda, if N is an integer, is divisible by lambda. Okay, or in other words, you're going to have, this creates, when this ray of light and this ray of light are out of phase by an integral number of wavelengths, by only whole wavelengths, then you're going to have constructive interference. So that's why you get this equation. If this one lags behind the other one by a half wavelength, then you're going to have destructive interference. All right. So that's another description of what N stands for, or M. This is just an integer. Just think of this as, it could be P, Q, W, J, L, element O, P. It's just an integer. And that's going to be a whole number, and this is an integer that's going to be a whole number plus a half. Just think of it like that. All right. So we are looking at part B, which wants us to look at the first bright fringe, where M equals 1. Okay, so bright fringe, M equals 1. So M equals 1. I've got lambda here. My lambda is 520 times 10 to the negative 9 meters. And D is still 1.4 times 10 to the negative 6 meters. All right. So I get the inverse sine of both sides. And what does that come out to be? To the negative 9 divided by 1.4 times 10 to the negative 6. Okay, and then get the inverse sine of that. Okay. I got 0.3714 something. And the inverse sine of that is 21.8 degrees. So what does that mean? That means if I angle it up, if I point my laser pointer and I angle it up at 21.8 degrees, I will find the first bright fringe for N equals 1. So not this fringe, because this one is N equals 0. I'll get this fringe, the second fringe, or that one. N equals 1. That's N equals 1. All right. Part C, the dark fringe, for which M equals 1. Okay, and I think you're probably getting the hang of this. So I'll just do C and let you do D on your own. Okay, so the dark fringe for M equals 1. We're not talking about bright fringes, we're talking about dark fringes. So we use this equation with the N plus 1/2. All right, so M equals 1. So that's going to be 3/2. You know why I said 3/2? Because 1 plus 1/2 is 3/2. Okay. All right, times 1 times the lambda, which is 520 times 10 to the negative 9 meters, divided by 1.4 times 10 to the negative 6 meters. Again, I take the inverse sine of both sides. What does that do? So that's 1.5 times that divided by 1.4 negative 6. Alright, and get the inverse sign of that. And I get 33.8 degrees. Yep. So that means that I need the angle, at an angle of 33.8 degrees from here, I will be looking at the first right fringe, for which m equals 1. Alright, so that's pretty much all I want you to know from that chapter. Alright, chapter 28. And the other equations work the same, okay? Chapter 28, special relativity. Okay, so again, let's pull out the sheet from chapter 28. Review mass energy transmutation, length contraction, time dilation, and make sure you understand the right reference frames for all the physical quantities involved. Okay? So here, time dilation is 28.3, length contraction is 28.4, mass energy transmutation is E equals mc squared, and what that says is that E equals mc squared is mass and energy are the same thing. You can convert mass into energy, you can convert energy into mass. And if you want to know how much mass you can convert into energy, I mean, not how much mass you can convert into energy, but if you want to know how much energy you get for a certain amount of mass, if you were to convert all of it completely into energy, then you use this equation equals mc squared. That's probably the most famous equation, you know, that people are familiar with, okay? But they probably don't know that what it means. They probably don't know that it means mass transmutation, mass energy transmutation, okay? So what do I want you to know from special relativity? When objects start to move at speeds that are close to the speed of light with respect to each other, you can't use Newtonian mechanics anymore. That means time is different for one. Time passes by differently for one person in that reference frame than for another. Okay, what do I mean? Okay, there are two postulates for special relativity. One is that the laws of physics remain the same in all reference frames, inertial frames. And the other one is that the speed of light is the same in two frames of reference. Two inertial frames of reference. What do I mean by that? Okay, so what is a frame of reference first? A frame of reference is a coordinate system and a clock in which events happen. Okay, so one way you can talk about it is, okay, if someone is sitting on a train that's traveling at a velocity v with respect to this person who's just standing on the side of the road, okay, this person, if this train is, this is called an inertial reference frame if this frame is not accelerating with respect to this guy here, the observer. Okay, so this is a passenger on the train, just sitting down. And say they're throwing a ball up in the air. Or they're just looking at a ball, just looking at they're holding a ball in their hand and they're observing that ball. Okay, they're just looking at that ball in their hand. How fast is that ball going with respect to this observer? 0. It's going at a velocity of 0 with respect to this observer. How fast is that ball going with respect to this observer? It's going at a speed v. So if v is 50 miles an hour, this ball that looks stationary to this observer is going at a speed of 50 meters per second with respect to this observer. Okay, now what if this guy, let's move from the ball picture to light. What if this guy measures, he's looking at light passing in this reference frame. In his reference frame, he's looking at light, he measures the speed of light. What does he measure? What's the velocity of light that he measures? Okay? He's going to measure the velocity of light to be 2.9 times 10 to the 8 meters per second. No. Before I get to that, let me do one more thing to drive it home, okay? Let me use one more object. Say a little puppy. Somebody's got their puppy running through the aisle, okay? So that puppy is running through the aisle, and say that puppy is going at a speed s. That's, let me put my velocity, it's the velocity of the train now, 50 meters per second. This driver scene is 50 meters per second. Okay, this puppy is going at 2 meters per second. How fast is the puppy going with respect to this observer on the train? 2 meters per second. All right. How fast does this guy see him going? 52. That's 50 plus 2. Yes. Somebody ask a question? Okay. All right. So now this might freak you out. Okay, what if I have light going? This turns into a lab where they're measuring light, the speed of light in this reference frame. The speed of light that they measure in this reference frame is going to be 2.98 times 10 to the speed of light in the vacuum, meters per second. All right. So we went from a ball to a dog. Now we're talking about the speed of light. At what? So this is a light coming from a lamp, a beam. It's a light beam coming from a lamp behind the passenger. So they measure the speed of light. They get it at 2.99 times 10 to the 8 meters per second. How fast does this guy see that light going? With the train going 50 meters per second. Okay, that's the strange thing about special relativity. That's where the strangeness comes in. Light is going at the same speed in this frame as it is in this frame. It's not like the dog where you add the velocities together. Like it's going at the exact same speed. And from that, because of that, all kinds of weird things, weird meaning all kind of non-intuitive things from our Newtonian